Good afternoon, everyone. I'm Yong-Deok Kim, and this is a joint work with Tae-Hung Jang and Professor Bo Young-han and Professor Seung-Jin Choi. This is the outline of the presentation. Okay, as we already know, training a CNN from scratch takes a lot of time. Fortunately, various pre-trained CNNs are fully available. For example, Berkeley University provides pre-trained AlexNet, GAFANet, and GoogleNet with GAFA framework. Oxford provides 5 different versions of the VGG model, and MIT provides AlexNet, GoogleNet, VCG, which are trained on the Places dataset. Not only university, but also companies share their valuable research results. For example, Microsoft provides 3 versions of the residual net, and Google provides the Inception v3 with TensorFlow framework. Recently, a bunch of research results show that these pre-trained CNNs can be successfully transferred to the new task. If the size of the new dataset is sufficiently large, then fine-tuning through end-to-end network is recommended. However, if the size of a new dataset is small, then to prevent overfitting problem, more simple approach that regards pre-trained CNN as a feature extractor and train a linear classifier is recommended. In this scenario, off-the-shelf classification algorithms such as support vector machine can be used, but it usually involves time-consuming cross-validation and research to identify good regularization parameters and to estimate the generalization performance. In this work, we propose simple but effective algorithm for transfer learning from pre-trained CNN based on the Bayesian LS-SVM, which is formulated with Bayesian evidence framework and the LS-SVM. This approach automatically determines the regularization parameters in a principled way and show comparable performance to the standard SVM, which is based on hinge or squared hinge laws. More importantly, Bayesian LS-SVM provides an effective solution to select the best performing pre-trained CNN or subset of pre-trained CNNs in a greedy manner. So I'm going to explain on the Bayesian least square SVM framework. We use the one versus all approach for multi-class or multi-label classification problem. And we use the least square laws and the L2 regularization parity. Hence, for each class, we will solve the Lipschitz regression problem, and this Lipschitz regression formulation is equivalent to the map inference of the isotropic Gaussian likelihood and isotropic Gaussian prior with hyperparameters alpha and beta. Someone may argue against the use of least square loss function for classification problem because it over-penalizes the well-classified example, but practically least square loss is often used for classification problem and empirically shows the comparable performance to the hinge loss. More importantly, this least square approach has clear benefit in terms of computational efficiency that it requires only one eigen decomposition to obtain this posterior and Bayesian evidence for all combination of the hyperparameters alpha, beta, and target variable y. So the Bayesian evidence can be maximized by repeatedly iterative this fixed point update rule. And note that I eliminate the superscript denoting the class for simplicity of notation and just explain the computation of the evidence for a single class. But because one processor approach is used, the overall evidence for entire classes is simply obtained by the summation of the evidence from these individual classes. And now with this overall evidence, we can choose the model with the maximum evidence, or alternatively construct an ensemble of CNN in a greedy manner. So previously explained, Bayesian evidence framework is useful to identify a good CNN for transfer learning and reasonable regularization parameters. To make this framework even more practical, we present a past algorithm to achieve the same goal and a new theory that guarantees the convergence of the algorithm. At first, the evidence, which is the function of the hyperparameter alpha and beta, is reparameterized to the function with the lambda and beta in this way, and it is reduced to the one-dimensional function, which is directly corresponding to the regularization parameter. As the figure in bottom right shows, this evidence function is neither convex nor concave. To maximize this non-concave and non-convex function, we derive a new fixed point update rule and present a sufficient condition of the existence of this fixed point by using this theorem. Note that the non-negativity condition on the input factor can be easily satisfied because of rectified linear unit activation function, and L2 normalization is the commonly used preprocessing. And finally, we accelerated this fixed point update rule by using the Aiken delta squared process. The figure in bottom center illustrates the Aiken delta squared process. Let's focus on the 2-point lambda 0, f of lambda 0 and lambda 1, f of lambda 1, and the green dashed line which passes these 2 points. The idea behind the Aiken's method is to approximate the fixed point by using the intersection of this green dashed line and put this blue line, which denotes the y equal lambda. As shown in the figure in bottom right, the Aiken delta squared processor is significantly faster than conventional expectation maximizer update or the original fixed point update algorithm. Okay, so as shown in the algorithm is summarized here, and as you can see, the algorithm is very simple and easy to implement. And most of the in this algorithm, we first compute the eigen decomposition of the XX transpose, and this is the most time-consuming part. But it needs to be performed only once because the result can be reused for any target variable y. So after eigen decomposition, we obtain the regularization parameter lambda through these iterative procedures. Okay, I'm going to present the experimental result. In our experiment, we used the 12 visual recognition benchmark data set and 4 pre-trained CNN in a Berkeley Cafe model. We used Google Net and VGG and AlexNet, and in the case of Google Net, we used the first Google Net is trained on the ImageNet dataset, and the second Google Net is trained on the Place dataset. In the case of Google Net, we extracted the feature from the global averaging filling layer, so its dimension is about 1000. And in the case of AlexNet and VGNet, we extracted the feature from the post fully convolutional layer, so its dimension is about 4000. So we first compare the performance of our Bayesian LS-SVM with standard SVM. For the SVM training, linear factors are used and regularization parameters are selected by grid search with cross-validation. As shown in this table, Bayesian LS-SVM is competitive with SVM in terms of prediction accuracy, even with significantly reduced training time. Especially, training SVM is getting slower than Bayesian SVM as the number of classes increase. But in the case of Bayesian LS-SVM, it does not depend on the number of classes. Another notable observation is that the order of prediction accuracy is highly correlated to the evidence. This means that the selected model by Bayesian LS-SVM produces a reliable testing accuracy, and the property representation is obtained without time-consuming cross-validation and grid search. We now show that our Bayesian LS-SVM identify a combination of multiple CNNs to improve accuracy without grid search and cross-validation. For each task, we select a subset of pre-trained CNN in a graded manner, and as shown in table, our ensemble approach achieved the best performance in the most of the data set, and the identified ensembles are consistent with the selection by exhaustive evidence maximization and even oracle selection made by testing accuracy maximizations. Okay, to conclude, I have presented on the past Bayesian LS-SVM for transferring pre-trained deep representation. It showed a comparable accuracy to the standard SVM, while its training speed is much faster. It can automatically select a regularization parameter in a principled way, and also select the best performing pre-trained CNN. Okay, that's all. Thank you.